Drawing resonance structures. Remember, resonance is important because it stabilizes a molecule. You will see in this class that a lot of reactions are driven by stability and instability or instability. Before you attempt to draw resonance structures, you need to remember a few rules. Number one, what changes in the resonance structures are only what we call delocalized electrons or electrons in the double bonds or in lone pairs. Notice here, I did not remove any atoms or switch them around. I only moved around the lone pair and the double bond. So be aware of that. You can never move single atoms or single bonds. You cannot do that. The second rule is that resonance structures must be valid Lewis structures. So you can't have all of a sudden you go from an octet to more than an octet. So if you notice in this example right here, when the electrons moved from nitrogen, that carbon right here has now 10 electrons. So you cannot do that. So what happens? Well, we're going to show you, you're actually going to have to end up breaking that double bond between the oxygen and the carbon. So you cannot violate the octet rule. Third is that the resonance structures must have the same number of unpaired electrons if they have unpaired electrons. So here you have no unpaired electrons. You have lone pairs, but you have no unpaired. All of a sudden now we have two unpaired electrons. That is not allowed. So again, octet rule, keep that in mind. You move only lone pairs and double bonds, no atoms, no single bonds. And of course, if no unpaired electrons if you didn't start with any. Okay, so let's go with practice here. So I left this blank because I would like to draw. It would be easier for me. But again, we're gonna, when we meet on the next day, Thursday, we're gonna start using these. Oops. We're gonna start using these with skeletal structures. So when you go on and examine the next lecture, the next topic on skeletal structures, make sure you're good at it because we're gonna now start using them with skeletal structures. So let's begin. So imagine you have this molecule. Okay. All right, you have to ask yourself a few questions in order for you to determine if they are resonance structures and then proceed to the next resonance and draw the next resonance structure. Number one is, do you have any double bonds? You have a checklist. Do you have any double bonds? Or obviously, remember, in double bonds, there are pi bonds. And if the answer is yes, okay, so you're most likely to have it. You have any lone pairs? And of course, charges. Well, if you recall, again, that's why you need to get the formal charges understood. There would be a negative on oxygen. Okay, then the next thing is, then ask yourself, is there a way I can actually move the lone pair into a double bond and then the double bond into a lone pair? And let's look at it. In this case, yes. So what do? You use what we call a curved arrow. So this can go in both directions. And that arrow goes, if you have a lone pair or a bond, you're basically taking it from where it is to the place that you want it to be at. So watch what I'm going to do. I'm taking, let's say, this lone pair. So now this lone pair is going to be now what? Between this carbon and the oxygen, but we know lone pairs only belong to an atom, so they would form a bond. Okay, now let's see. What happens if we leave leave it like this. Once again, this is violating the octet, more than the octet. So you say, okay, well, what do I have to do? Well, what you do is you break this double bond. So now you're moving these electrons from the pi bond to the oxygen above to form a lone pair. So I'm going to erase these arrows. And show you the final product. Okay, now here it is. Now be aware that you have a negative charge. It was on here. Where should it be now? Remember your honk 1, 2, 3, 4. When oxygen has only one bond, then that's a negative. Or a way of remembering it is whatever, wherever the lone pair came from, the negative charge now will switch place with the other atom. So it was here before. Now the bonding changed, so it must go on this one. Now, can you draw another one? Can you draw another resonance structure? And notice the arrows that I'm using here. No, you cannot. If you try to move some over here, they can't jump. They can't take a big leap like that. So you're done. You only have 2. Now, let's go to another one. Okay. Here it is. So ask yourself, do I have any double bonds in this one? Are they near each other? Yes, I do. Do I have any lone pairs or charges? Yep, I have a charge. I have a positive. So then what can you do? Is there a way you can move the electron somewhere? Yeah, so you can move this bond over here. I'm going to put the arrow up, down like this. Okay, so I move the double bond now between these two. And now, okay, where's my positive charge? Where's the positive charge? It's now on this one right here. Why? Once again, you can't just choose and say, okay, the positive charge or the double bond has to be here, positive there. Remember, there's a hybrid, right? You have all of these structures in one or occurring in one. So positive from your formal charge is carbon with 3 bonds, no lone pairs. That would make it a positive. When we come on Thursday, we're going to do more complex examples. So in the meantime, you have some practice and you will go over them and write down any questions you have. But we will go over more complex one. We're going to be in for the whole time on Thursday. And in the meantime, feel free to consult other resources.